Good afternoon and welcome to Tech Knowledge series of webinars with today's topic being how accurate are your FEA results? Today we have a special presentation from Mr. Natarajan Ramamoorthy, Managing Director of EGS India, on his favorite topic, Finite Element Analysis. With over 39 years of experience in the field of product design, development, verification and validation, Mr. Natarajan brings rich experience in solving real-world problems. Since inception in 1993, EGS India has been known for its FEA capabilities. Mr. Natarajan started his career with Ford Motor Company, USA, in Ford Scientific Research Laboratories as a structural analyst specializing in FEA. Over years at Ford, he worked on developing new technologies, products that incorporated advanced FEA capabilities for mainstream design verification. With strong experience in real-world correlations, Mr. Natarajan has taught FEA for postgraduate programs and continues to inspire the next generation of design engineers in acquiring best-in-class technologies and processes. Every presentation of Mr. Natarajan has many elements of new thinking, innovation, and practical problem solving. We hope you enjoy this presentation and benefit from the same in your professional life. Over to you, sir.
Thank you. Good afternoon to all of you. Greetings from EGS India. Today's presentation is going to be on how accurate are your finite element results. Finite element analysis has become a mainstay in a lot of design verification across varied industries. I hope to touch upon a few points which you may not have observed or seen and bring home some new technologies and concepts that I would like you to incorporate in your finite element analysis so that the end result provides you with confidence that the product would live up to the expectations in terms of fit, form, and function. Before we do that, let me introduce the company, which started in 1993. Vision was engineering development through effective partnership. We try and achieve the vision by providing the mission in terms of imparting leading edge technologies, training and development, problem solving and new product development, and providing software solutions and technical support. Since 1993, we have been doing three different functions: engineering services, software sales and support, training in these are the three verticals in which we exist. Engineering services is our mainstay where we develop new products and technologies for many companies across India and the rest of the world. The company in India was started with the mainstay of providing indigenous technologies to companies in India that are seeking world-class product development. Second one is there is no point in doing product design development without verification as a part of it. So finite element analysis, computational fluid dynamics, tolerance stack-up analysis, dimensional management, all these areas we adopted a lot of different technologies over a period of time, working on varied products so that the verification of design can be done in confluence with all these different approaches. Then value analysis and value engineering is a mainstay in most of our design and development of products, whether it is machines, whether it is automotive sector, defense, whichever we talk about. On the software sales and support, we have been associated with Dassault Systems since 1999. So that brings us what, 27 years of association with them. Over a period of time, we have been developing a lot of, we have been implementing product design, product data management, product lifecycle management. With those experience, we started developing our own tools and technologies indigenously in India. As a flagship product, Live QC Tools, which is a quality management system, has been launched last year, April. 1 year we have completed. Design automation and CAD automation are something, customization is something that our team does day in and day out with the active set of customers working to improve their productivity in their organization. And then academics is a well-known training institute from us, which provides mainstream training in the areas of core engineering functionalities relating to geometric dimensioning and tolerancing, tolerance stacks, which comes under dimensional management, failure modes and effects analysis, design for manufacture, design for assembly, finite element analysis, and CAD, popular CAD softwares like SOLIDWORKS. Now, when we get into how accurate is your finite element analysis, the first thing we need to understand is the objective for performing the finite element analysis. Is it the first time you are developing a product, as a result of which you would like to assess the failure modes and see whether the product is going to live up to the functional requirements? Or are you performing a finite element analysis as a part of a post-mortem when a failure has occurred and you would like to do a root cause analysis to investigate the causes and provide remedial measures? These are different areas in which finite element analysis finds usage, either in the new product development upfront, when no prototype has been developed, or subsequently when things have gone wrong, how to correct them. These are the two areas in which they find mainstay. Now, prediction versus reality. If we are going to be talking about prediction, upfront engineering, concurrent engineering, simultaneous engineering, whichever name you call it. When I was working at Ford Motor Company in 1989, Ford coined this word simultaneous engineering, wherein manufacturing, downstream vehicle integration people, as well as design, along with the suppliers, would sit together, brainstorm, get things sorted out before the drawing is released. What happens after that? The drawing never goes through a revision for another 3 to 4 years. It will be in 0, so that 4 years later, let us say we are doing a suspension spindle. There's a change in the anti-lock braking sensor. It moves from position 1 to position 2 in a new model of the same car. Then it would go through a revision a second time, and that would take a little bit of time for them to ensure that nothing else has been treaded upon, and the drawing would be released. So in other words, every time a drawing is released, it costs the company money in terms of retooling, in terms of revalidation, re-verification, so many things. Your production part approval process, your advanced product quality planning, every one of them have to go through a change, right? Now imagine if the change is going to come as a result of a durability issue, either because you saw it coming, or it came after the prototype has been developed and it was tested, or it came when the customer came and complained. Either which way, finite element is the only thing that people need to rely upon at this point in time, so that they can look at what went wrong and to provide corrective actions. So typically it is done for performance. But when the physical failure occurs, it could be because of loading, it could be because of material or manufacturing defect, or assembly related variations, or it could be the environment, the product abused by the customer, or a combinatorial event which comes in from all the different aspects that could have come in to play in alignment, or any other extraneous factors like the act of God. So when we look at all these different combinations and when we are doing a finite element analysis, the finite element analyst who steps into the shoes of the design engineer to verify the design needs to be circumspect about all the potential combinations that would come about, that the product would experience in its lifetime, and then simulate the same thing, right? So when we are looking at the prediction, the more and more we build a predictive model which is realistic, the more and more you will be in a position to say, my design is more reliable now. Typically, people look at finite element analysis as a part of durability. When you look at any reliability textbooks, they look at finite element analysis as a part of durability, and they give a 1-page contribution in a book which is 500 pages. The rest is all related to reliability calculations, either in series or in parallel, or series and parallel together. But unless the finite element part of it is brought into the variability of the process or the product, the reliability cannot get enhanced. So this presentation is more to do with how accurate your design is going to be to predict the performance and or the failure upfront a priori before the first prototype has been launched, not after the failure has occurred. Nevertheless, you can use the same concepts in a post-mortem or a posteriori activity, but nevertheless, it would be cheaper if this was done earlier up in the design phase than as a post-mortem. Now let us take a look at an example. You are looking at the sheet metal subframe. For people who are not associated with the automotive sector, this is typically the product, the assembly on which the engine sits. Okay, the integration of the suspension, the integration of the steering system, the lower control arms, the engines, everything comes on top of this subframe structure. Now, if I were to be asked to look at this structure in totality, and if I were to be the finite element analyst who is going to go about doing this analysis to predict accurately, what are the different things I would consider? Other than the load cases that would come from the OEM or from the torture track or from previous database, the first thing I would be looking at is the stiffness. Second one is the strain state. I am not talking about the stress state here. Did you notice? It is the strain state. Why? Because stress is nothing but E epsilon, right? E is your elastic modulus. Elastic modulus is an approximation of the slope of the stress strain curve. I repeat, it's an approximation. So the strain is accurate while the stress has its noise in terms of the elastic modulus. 99% of the industry looks at stress-based finite elements, not realizing that elastic modulus is a noise which is coming into picture. Even a 5% variation in the elastic modulus, you are going to have trouble. Believe me. So when you are looking at the strain state as a result of the load, the strain as a result of the assembly, and strain as a result of the manufacturing of the individual components that come into the assembly. I'm looking at it in the reverse as compared to the list that was provided there. Normally, we look at the strains on the load. We look at the assembly strains sometimes. But do we really look at the pre-strain that the system has inherited even before the first loading came into existence? Hardly so. So then how can we look at life expectancy in a reliable manner? So the reliability comes into focus when we are looking at the finite element analysis of this. So all the variations, the load variation, the dimensional variation, the assembly variation, the material variation, the way the system is getting fitted onto the car, the variation in that, all those come into picture when it comes to the reliability. Now, if you look at the cross section that is given over there at the bottom, you will see it's a deep drawn part. So the part has to go through multiple levels of stamping, drawing operations, right? So which means, let us say it's a 3-stage unit. And I have been told by manufacturing that they are trying to reduce the cost to win the order. So they are going to go from a 3-stage stamping to a 2-stage stamping. Imagine taking the chapati dough and putting it through the kneading process with hard pressing and rolling and stretching it. You will get the tear, right? If you do it faster with a larger load, same thing happens here. When you feed in just enough material and you're trying to put it through 2-stage instead of the normal 3-stage because you want to cut the costs, your thinning would come in, significantly reducing the overall section modulus, increasing the pre-strain state. Are you with me? So are we taking this into consideration? Now let us say in certain areas on the subframe, we are also doing welding, spot welding, seam welding, continuous welding, submerged arc welding, so many different types would come in. Then what are all the pre-stress raises that are coming as a result of this? As a result of the manufacturing process. They are not quantifiable, right? It's not visible to us, right? But we need to take care of them and ensure that those are not going to either affect, or if they are going to affect, how we are going to alleviate them. So When we are doing these kinds of analysis, we need to look at the sheet metal thinning that would happen. A 10% thinning on a 3.4 millimeter thick plate brings down to 0.34, right? Which is 3.06. But you have done a nominal analysis with 3.4. So there are two stages that you need to look at. One is the bought out raw material, 3.4 plus or minus 0.2, let us say. So 3.6 to 3.2. If 10% comes from 3.2 material fed in from that particular lot, imagine where you're going to be with the two stage. You will get shrink bands, you will get pre-stress states coming in and alarmingly saying that you are going to have problems, which means my section modulus has to be assured for all these variations that are going to come into picture a priori. You may say that it is not the design's responsibility to do this. But if there is a failure, who is going to do the investigation and who is going to correct the drawings to ensure that this problem is mitigated? It is design. Might as well do before it arose as a part of a process. Next one is the sheet metal stamping spring back. You would have given a profile tolerance on the drawing. The spring back is included, is accommodated in the profile tolerance that you have provided on the GD&T drawing. Is it within that requirement or not? The near net shape that you wanted the product to be in, is the manufactured part adhering to that near net shape that you want, or the shape is completely different? When you do a DVPNR, design verification, planning and reporting, in that dimensional verification, planning and reporting is also there, right? First article inspection. When you take that profile and you look at it and it's not conforming to the what you have given on the drawing, is it because of manufacturability or is it because of tooling deficiency, or a combination of both? What is going to come and haunt? The product performance is going to be haunting, right? So when we take a holistic look at any particular component that is going into the assembly, we need to capture the state of stress when it starts performing, with two combinations coming in, one inherited as a result of the manufacturing in the assembly process, the other one as a result of your loading conditions coming in. Now, if we are to do the subframe FEA verification, you would have a static analysis, a fatigue analysis, an NVH vibration acoustics analysis, a crash analysis on impact, and topological analysis in terms of optimization. Right? These are the different things that we look at. How accurate are our procedures? How accurate are our results? How accurate are the interpretation of the results in every one of those silos that we are looking at? Remember, each and every one of them is interconnected here, though they have been shown as different islands. So if you take the pre-stress which is coming in the 7th, the joint weld and the integrity that is coming in the 6th, the thermal and the corrosion part of it which comes subsequently down the line, we have a whole new picture emerging. So when a finite element analyst is looking at the design, he or she has to take into consideration the complete aspect of how that part is going to be in the assembly, or how that a sub-assembly is going to be in the main assembly, and look at the gyrations it would go through and predict the durability based on that, thereby enhancing the confidence in terms of the reliability. So the typical analysis sequence you would put together, and you will see this. In every one of these analysis, there is an assumption, a boundary condition assumption, an isotropy assumption on the material product, right? Now, when you look at the subframe itself, it is going to have grains being in one direction so that you exploit the best capability. I am asking a question to you. Are you using an isotropic model, or are you using a grain oriented orthotropic or material anisotropic model even for a sheet metal component? In other words, directional material property according to the direction of the grain as it comes in the rolled sheet has to be taken into account because it influences the stiffness through the percentage elongation. We give the Poisson's ratio, we give the elastic modulus, and we forget it, right? But then your percentage elongation matters quite a bit, right? The ductility of the material in terms of its ability to absorb the energy. Then it needs to be factored in, means your grain direction has to be considered in your isotropic analysis, in your normal material property analysis, especially if it is sheet metal. That is where most of your accuracy goes for a toss. Then comes point mobility. So many different things are there. So the clarity with which we do the analysis at every stage, it is not the analysis just because somebody wants a report. It is an analysis because we want to give the customer the best performance for the cost that he is going to incur, the price he is going to incur. If you want to reduce the cost of ownership of the customer, if you want to reduce the cost of quality for yourself, obviously this process has to be sterilized so that the accuracy improves multifold. The models what we are showing in this presentation are generic models. They are not customer models. So you can be rest assured that the customer confidentiality is not being exposed because we are covered by customer confidentiality. This is an interesting problem that I would like you to look at. You have a rim which goes through a rolling process. So there is a pre-stress state coming into picture, a pre-strain state already inherited. Then you have the disc which is stamped into position. Then the rim and the disc have an interference. They are assembled together and then they are welded together to form the disc wheel, right? So what are the things that we are looking at? We are looking at the stiffness. Stiffness during what? Lab stiffness, stiffness during operation. If it is stiffness during operation, the next question I will ask you is, have you considered spinning stiffness? When the object spins, the stiffness changes. Spin softening takes place. Have you considered it? So the stiffness, it would vary as a result of what? Thinning. It would vary as a result of what? The profile that you have given, profile tolerance. It would vary as a result of what? The grain of the material. Sir, elastic modulus is what we are looking at, sir. But percentage elongation? The strain energy under the curve? You are saying. I am asking you to look at it one step further. If you are looking at deflection on a wheel when it is loaded and you're using a dial indicator to get the value, your deflection between finite element analysis and your physical testing should be 99.99% accurate. Finite elements can give you that. So next thing is the strength of the material, the flexural rigidity of the material, especially on the rim side, the fatigue life, whether it is the rolling radial fatigue test or the cornering fatigue test. And then comes the acoustics in terms of interaction. Now, if you take a sheet metal and you stamp it and then you weld it to a rolled sheet metal and then you put the tire on and then you simulate the inflated tire condition and then you apply the load, can you do this progressively, one after the other, so that the inherited stress state from the first stage comes of use in the last stage? Can it be done? Absolutely. Today, technologies are available for you to do that. You can do what is called as the inherited pre-stress state. Now, the thinning due to the stamping can be captured. The pre-strain due to the disc stamping, the rim rolling, the rim disc interference can be brought into the picture. Then you can predict the fatigue life better. Why? Because you will be doing the mean correction. This influences the mean. And because of thinning, the amplitude could be changing succinctly over there. Years ago, we did work on alloy wheel for an American company. I can tell this now because it is beyond the confidentiality period and the vehicle has already been launched in the US. And one of the things they were surprised was, typically tensile cracks is what people look at. In that case, right next to the hub area, the fissure cracks came in, which is in compression mode. We were able to predict the compression cracks. Those cracks may not propagate, nevertheless, they would be there. They were surprised that we were able to capture the fissure cracks, which would not really create a problem as compared to the tensile cracks, and both were correlated to less than 5,000 cycles. Then the tire interaction in terms of the acoustics, in terms of moving away from the tire acoustic noise things. Can it be done? Absolutely. Then the stress stiffening effects, incorporating the grain direction, thinning, and the tightening torque. When you are taking the frequency analysis, if you are applying the tightening torque, you will get a frequency. If you are applying it just impulse hammer car, normally placed wheel without any pre-tension on the bolts, just simply placed, you look at the impulse hammer test, you will get a 10% variation. Can you believe it? 10% variation. Can finite element predict it to less than 0.1 hertz? Yes. That is where we learn how the system operates. So you look at all the different aspects of it, put it together, as the sheet metal would have finally landed up as a wheel. You take this component through the manufacturing process on the digital simulation side, and then you look at the predictive life cycle of this. This example I have shown you only because all the different aspects of manufacturing which influences the fatigue life needs to be taken into consideration by design. You cannot apply arbitrarily a 10% thinning on the model and you cannot run the analysis. That would mess up the durability quite a bit in terms of the stiffness and in terms of the node and the anti-node positioning on the disc and the rim. You cannot do that. The fixity will get into problems. Now, the next example is, now till now we talked about stiffness, we talked about static stiffness. Now we are talking about dynamic stiffness. In a mount, you need to look at the dynamic stiffness. You do the point mobility studies. You look at the directional mobility and you look at the target stiffness versus the actual part stiffness versus the FEA response, frequency response function. This needs to be looked at. Years ago, we did a project for a company which had 7 manufacturing locations worldwide. We took 13 of their mounts and redesigned those mounts and revalidated those mounts and did the optimization of those mounts. Today, you have the capability to do shape optimization inside finite elements. Now, artificial intelligence is breathing down the neck again. So the day is not far off when the AI tools start giving you optimized things which don't make sense when it comes to looking at the topology. Abstract modeling, that kind of thing. So the elastomer steel bonding, why is it required? The shear in that area, if it rips open, your mount is gone. So the aging considerations, the manufacturing pre-stress, the assembly pre-stress, when you are bolting it together, this changes the frequency completely. So now in your finite element tool, you need to go from end to end, build up the capability, because this is what is the technology that you need to acquire so that you know, like the palm of your hand, how your product is going to function and where the risks are with regard to a particular decision that you are taking in terms of cost or in terms of time, because it affects the quality of the product subsequently down the line, right? So these decisions cannot be inimical to the CTQ. Now take a look at this picture. You will see a reactor column sitting. If I look at this, I will throw tantrums, but this is how typically petrochemical units are. Now, we had a condition wherein we had to look at the external disturbances, internal disturbances, the combination of external and internal disturbances that would wreak havoc. For example, the person who did the finite element analysis here forgot to look at it as a system and did only tube bundle vibration according to a manual calculation and then small FEA with the beam analysis. When you look at the complete system, the tube bundles which are rotating, they started failing. Here, the requirement is temperature and displacement. Now remember, in conventional finite element analysis, you do displacement as the unknown variable, right? From there, you get your strain field and then the stress state. That's the displacement based finite element method. Then you have the single degree of freedom of called temperature. You go through the conduction, convection, and radiation equation, heat balance, and you solve the problem separately. What if the temperature expands? As a result of expansion, the stiffness changes. As a result of stiffness, the displacement changes. Then what happens? Then the stiffness is completely different, right? If the stiffness is different, the deflections are different, the strains are different, the stresses are different, the cyclical fatigue life is different. The tube bundle vibration problem, now the stiffness has changed, the frequency has shifted. So in the cold condition, when you did the analysis, everything was hunky-dory. Then in the operating superposition, you didn't have a problem, but then you didn't do a coupled analysis, you get into trouble. So when at any point of time, linear superposition people do, but what about the cross correlation matrix that goes between one recursively influencing the other? Add on top of it aggravation by stresses in assemblies because of corrosion. Normally, what do? We apply a corrosion factor and increase the schedule. Now, what is it going to affect? It is going to affect the thermal balance. It is going to affect the natural frequencies of the system. It is going to affect the frequency response function of the system. It is going to increase the cost of the system. By increasing the schedule, we are not doing a cost engineered product, are we? In this case, if I were to increase the schedule, the cost will go up exponentially. Who's going to pay for it? We are going to be not competitive in terms of pricing. The market share will come down. So any kind of heat exchangers, it involves fluid, structure, thermal, all three put together, the confluence of all three. Today technologies are available where you can easily build models which can go between the different domains and give you a complete picture as compared to staggered picture in each and every one of them separately. I'll give another example. You have tubes bending inside. When the tube bends, what happens? The thinning of the tube takes place. Now the stiffness has changed completely. The strains, pre-strains that are coming in as a result of the bend has now come in. I'll give another example. Long tubes are being put into the system. You don't have intermediate supports. Why? Because it is influencing some performance, or because it is difficult to fabricate. So you have only end-to-end support for the pipes. Now the fluid, the viscous fluid is flowing through this tube bundles, and it is also getting heated up. Now the tube sags. Now there is an external strain which is coming in as a result of the sagging. It may be minuscule, but over a period of time, it reduces the life of the equipment. How did we consider it? We are tightening we are doing end treatment on the flanges for the pipe. It affects the stiffness because the end stiffness gets affected now. How are we capturing that? Are we capturing a stress field state or the stress field state? How does it influence? It depends on your failure modes. So let us take the example of a simple drop arm which is used in a steering of a car. Single part. I am taking a single part because I want you to understand that it is a part of a system. And when it is a part of the system, the component cannot be divorced from the system. And you need to do a system analysis, not a part analysis. How do I force this? Look at the DFMEA. You put the DFMEA in place, you start looking at what can go wrong with the design. Look at the severity, the occurrence, and the detection, and then you do the mitigation saying, I have already done the finite element analysis of this. I have taken this into consideration. So now the accuracy of your prediction is enhancing. Primarily, you are going to look at all the failure modes as documented and also looking at the cross correlation between the different failure modes. That is important. So once you bring in the design FMEA, what can go wrong with the design, and you do the analysis for every one of those DFMEA as it is required, then you link it with the process FMEA and you start looking at how you are going to reduce the thinning, how you are going to reduce the pre-stress coming as a result of the forging operations or the bending operations or whatever it is. Are we going to do a stress annealing? Is it really required? Justify it. Now you started predicting the accuracy even more better. And then which process can lead to or fail to prevent the design failure condition that we looked at? Have we mitigated all those? Then the third FMEA is service FMEA. Normally we look at only two, folks. Please look at the service FMEA as well. Now in this particular example, what does it say? Inspection of the boot seal condition. Why? Because the lubrication is happening because of that. The teeth failure will happen because of lack of lubrication. Lack of lubrication because of the boot getting punctured. The boot getting punctured because it was stretched in the articulation. It was stretched into articulation because of what? Because of the elastomer getting into position and the crimping that took place prior to that. And the crimping led to a pre-strain, leading to a boot strain, leading to a lubrication problem. You are supplying the unit as an assembly. You are getting the boot from the supplier, but you are assembling it. Your drop arm is your assembly. Now who gets blamed? So unless we get the pre-strain conditions, somewhere we have to start. Incrementally go through every one of these pre-states conditions and then put it together. Remember, when we come to the office early in the morning, we are in a pre-stressed state. Depends on how we slept, right? Every day. Similarly, our objects also go through the same conditions. It is only by building a painstaking predictive reliability model that we can say that the accurate state of stress has been predicted by us, so that the prototype testing can be few and far between. So the setup for FEA based on the severity, occurrence, and detection in the FMEA. In this particular case, again flexural rigidity. Then the life calculations for the LMC condition, least material condition. We always do it for the nominal, right? Based on multi-axial fatigue, because the component is bending in two planes, not in uniaxial fatigue. Then the spline wear, then the drop arm permanent deformation because of the limit load, then introducing the material orthotropy in terms of the grain direction, then pre-strain due to forging and the heat treatment, and wear in the conical ball joint area, specifically, especially because the ball joint gets pre-stressed, getting into compressive stresses over there. Then obviously corrosion, effect of inadequate pre-tightening torque. We did have a drop arm calculation wherein one of our customers asked us, this drop arm, can you please predict and tell me whether it failed because of lack of pre-loading or because of torture track issue. So we did the analysis both ways and we said it is not because of preloading, it is because of the cross-sectional modulus. And in this torture test track, between this cycle and this cycle, you can go and see the truck would have this component, this particular area, the crack would happen. They were shocked. We didn't know it. We predicted it. They came back and said, how did you do this? This is the process. So instead of doing a simple static analysis, which doesn't give you a whole lot of things, I'll give another example. Years ago, we were working on high-speed bearing testing. High-speed bearing means the bearing, high-speed bearings are 70,000 RPM to 1 lakh RPM, 1,10,000 RPM. We were using a friction disk. The friction disk was rotating at 70,000 RPM. Typically, when a disk rotates at 70,000 RPM, we expect the hoop stress, the tangential stress to be high, right? No, the stress at the center was highest. Why? Because it was pulling the material from the center towards the edge. So finite element analysis is a confirmatory tool. People try to use it as a diagnostic tool. No, the diagnosis still lies with you. So the combinatorial analysis needs to be done for the usage function requirements based on design of experiments. And then the maintenance of tolerances post-heat treatment can all be studied using finite element analysis. Only when you put this together and look at the risk factors and you get in, then your result becomes accurate in terms of predicting the reliability and the performance of the unit in real world life. So incorporating the PFMEA, you put it upfront, residual analysis, forging, tempering, quenching and tempering, induction, and then short peening. You put that together and then you do all your analysis inside. Your inherited stress state comes in. It gives you a better picture. So in summary, the accuracy in finite element depends on how good we are in capturing the failure modes and linking it across design, process, and service. That's where your FMEA comes into picture. Emphasis on system level analysis, not component level analysis. Why? Because it is energy. The concept of Newtonian statics is gone. It's dead. Continuous system requires Lagrangian approach. That's what finite element gives you. So energy approach. Establishing correlation between variables to ensure the nature of independence. Severity analysis for combinatorial factors. Assessing invisible life-threatening factors. Factoring the material variation in terms of grain direction, in terms of non-metallic inclusion, things like that. Incorporating what-if scenarios involving process and service failures, and then considering piece part variations due to tolerances and the process health. All this, when we put together, your accuracy comes close to the bullseye. The benefit of this is enhanced durability, improved reliability, increased customer satisfaction, reduced cost of quality, unparalleled reputation for your product, technology, and your company.